Okay, this is the second video in our nuclear energy series. We're building up to be looking at fission and fusion, but today we're just going to look at binding energy. What is binding energy and how does it link to nuclear stability? So first up, let's do a little thought experiment. If we split up a carbon-12 nucleus into its nucleons, so here we go, let's do it. So there's carbon-12, and imagine that we are pulling out all of the protons and all of the neutrons, so hopefully we're going to end up with 6 protons and 6 neutrons. So on the right hand side you can see all of the separated nucleons. So our nucleus has now gone. It's well, not gone, it's just been split up. Let's just think about some questions. What force is being overcome to do this? Hopefully you'll remember it's a strong nuclear force that's holding the nucleons together, so we're overcoming that. Would we have to do work? Well, of course we would. We'd have to apply a force over a distance to pull those nucleons out, and we'd be doing work against a strong nuclear force. So therefore, has the potential energy of each nucleon been increased? Well, yes, it has. They're at a higher potential energy because the strong nuclear force would attract them back together if we let it. So if we've put energy in to do this, what should happen when we put the nucleus back together? Well, when you put the nucleus back together, we would get energy out because all of those nucleons would be attracted back together. So what should happen to the mass of the nucleus? Think about what we talked about last lesson, E equals mc squared. Well, it will decrease. Remember, if when you put the nucleus back together, if energy comes out, therefore the mass decreases. So the mass of the separated nucleons is more than the mass of the nucleus. That is absolutely key to today's ideas. All right, so let's just think about that. The nucleus forms, energy is released, it's equal to the energy needed to separate it, and we could use our formula E equals mc squared to calculate that, because we know that the mass of an object increases or decreases when it gains or loses energy, and this is the idea as energy having mass. So the big one here is the mass of the nucleus must be less than the mass of the nucleons. That is absolutely crucial for your understanding of binding energy, and this is called the mass defect. The difference between the mass of the separated nucleons and the mass of the nucleus is the mass defect. Now we could write an equation for this. This isn't on the data sheet, but let's just have a look at it. The mass defect is equal to Z mass of the protons plus A minus Z mass of a neutron, that's the number of neutrons, minus the mass of the nucleus. So if you take all the protons, add them to all the neutrons in terms of their masses, then take away the mass of the nucleus, all of that will give you a bit of mass left over, and that is what's known as the mass defect, which is the difference between the mass of the nucleons and the mass of the nucleus. All right, now the binding energy of a nucleus will therefore be this delta mc squared. Be careful, always check if you're given the mass of a nucleus or the mass of an atom, the difference being the electron. So you may or may not have to knock off mass of the electrons when you're doing your calculations. Okay, so let's do a bit of a question to demonstrate this. Find the energy released in joules and electron volts, if we need to, in the formation of a helium nucleus from its constituent parts. So here's our, given on the data sheet, we've got mass of a proton, neutron, mass of electron. We're given here the mass of a helium-4 atom. So I've underlined atom to make us remember. I've got some information. I've got 1U equals 1.66 times 10 to the minus 27 kilograms. I've got our binding energy idea, and here I've got our mass defect idea. So let's put something in for our mass defect. Our mass defect is going to be the number of protons plus the number of neutrons minus the mass of the nucleus, but remember here the 4.00260, I've got to take off 2 electrons from there. So here's my 2 electrons coming off the mass of the nucleus. Loads of numbers to put in your calculator. Have a go, do it. It's very easy to get this wrong. Think about the position of your brackets, but if you do it all correctly, you'll end up with a mass defect of 0.03040U. We can then we could use binding energy is delta mc squared if we want. So I'm going to convert 304U into kilograms. There's my conversion. C squared to give me 4.54 times 10 to the minus 12 joules. And then what we could do here, if you wanted to do it the other way, we could just use the conversion of 1U being equal to 931.3 mega electron volts, and here I could say that that is 28.3 mega electron volts. Okay. 2 two more quick questions. So if this was a helium nucleus, I'm not going to spend time going through these, but you can, if you want to pause it, you can check it yourself. Find the mass defect in U of a gold nucleus, and I'm giving you a gold atom here. Find the mass defect in U and binding energy of a carbon 12 atom. I'm giving you the 12 atom here. The answers are just appearing in red. Please again pause and check if you want to, because I'm about to use the three that we have just calculated. So we've done helium, gold and carbon. Okay, so we're going to use these numbers now. So how does all this relate to nuclear stability? Well, to compare different nuclei, we've just worked out three different nucleus mass defects. It might be worth us to look at the binding energy per nucleon. So we need to consider the total binding energy and the number of nucleons. In the three different nucleuses we've done, they've all got different numbers of protons and neutrons, different mass numbers. So let's try and have something we can compare by working out the binding energy per nucleon. Now, the binding energy of different nuclei are different, but the binding energy per nucleon is the average work done per nucleon to remove the nucleons from the nucleus. And this is a measure of stability if you think about it. Okay, so let's do, we've just done helium, gold and carbon. Here we go. Helium was 28.3 mega electron volts per nucleon, divided by 4. There's our answer. Gold, divide our answer by 197, and carbon, divide our answer by 12. Okay, so we've got 7.1, 7.9 and 7.7. So in terms of which is the most stable, well, the nucleus with the higher binding energy per nucleon is more stable. So in our case, it's gold. Gold is more stable because you have to put 7.9 mega electron volts per nucleon to separate that nucleus. For helium, you only have to put in 7.1. So because you're putting in less energy, that means the nucleus itself is less stable. The more energy you'd have to put in, the more stable the nucleus is. Okay, now what we can do is use a graph of all these binding energies. We've only done three, but if we have a look at a graph, this is a graph of the average binding energy per nucleon for loads and loads of different isotopes. And here you can see a number of nucleons in the nucleus. So you've got uranium over here. We've just done helium around here, and then some of the other ones you might be able to find carbon. There's carbon 12, and the graph gives you this shape. Okay, now let's just think about some of the things we can learn from this shape. What we're saying is that if you were to split up a uranium nucleus, then if you were to split a uranium nucleus up in nuclear fission and then make two lighter, then you're going to get energy released, because you'd have to put in this amount of energy per nucleon to split it up, but you would get out higher amounts of energy per nucleon. And this is exactly why we do fission and fusion later on. Fusion, if you think here, fusion, you're going to be taking helium and fusion, you're taking hydrogen and making helium. So you're moving up this graph, hydrogen, helium, or even a fusion of helium into something else, into like lithium. You're going up this graph, so you're releasing energy. But we will come to that in the next little video. Just to finish, you do have to know this graph for the exam. This is kind of the exam point, so what to include in an answer. Here's a basic sketch. You need to know the values on the X and Y axis. So binding energy per nucleon, it peaks here at approximately 56. This links into your work in astrophysics if you know about iron, but we'll come to that in the astrophysics lesson as to why iron's the most stable. And this graph is telling us why. So you need to know values on the y-axis, values on the binding energy. It's a best fit. There is an anomaly that's helium, so you should really show helium if you can. The graph really can't start at a equals 0, because if a is not at least 2, we have no binding at all, but that's a minor point. Both axes must be labelled for the graph to mean anything at all, and examiners expect numbers on the axes so the line can peak at the correct point. Okay, so that's the style of graph that you would need to be able to draw from memory for the exam.